Right, okay, so we're going to look at a dynamic data structure. Remember, a dynamic data structure is one that we don't know how big or how much space we're going to need when we write the program. The opposite of that is a static one, and a static one is where we do know the size. So in most traditional languages, if you create an array, you have to say how big the array is going to be. As things have moved on, arrays can be dynamic as well. Okay, and you can create arrays at runtime, which is what you do with the tile maps. Okay, those people that are using tile maps, we create those as we work along. They're not truly arrays. Okay, but we're going to look at the most useful dynamic data structures. The first one is called a linked list. Alright, and we talked at the end of the last lesson about records, because what we're talking about is holding multiple pieces of information. Okay, so we formulate that into a record. In object-oriented languages, you might make a class or a structure to hold this data. So we're going to have a record format. I'm just going to call it stuff. Okay, and we're going to have some data, and we're going to have a link. Okay, for this record structure. What I'm going to do is I'm going to show you what it looks like dynamically. Okay, so we would have a head. This pen's not very good. A head reference. They always look good until you start using them for more than 1 second. They've let you down. Right. So if we have got no items, what was that? It's all on video, Gary.
That's like all my ex-girlfriends.
Richard. It's not a care and share session.
Pretty quick.
Although it would be a not care and share session. Right. So if we have got no items in our list, what do you think? This becomes a pointer, this head reference, just like when we talked about the trees the other day, root node. Right, the head reference, what does it point to if there's nothing? Do you think? There's no items in this list.
Next bit. 0.
Nope.
Does it bring up an error?
No. Okay.
Whatever random stuff's at that location.
No. If we haven't got anything to reference, what do we use? What do we use as nothing when we're talking in programming terms? Null. Okay. So if we have nothing, sometimes we represent null with -1. Okay, and the exam board will let you use either term to represent pointing to nothing. Alright? But if we want to create something, and we're doing this dynamically, we say, right, okay, we want to store some data. So let's say we've got a name. Okay, and that's what information we're going to store. And we're going to store names alphabetically in this linked list. Okay, so we come along and we want to store, let's start with Dave, as usual. We create space. So we ask the operating system, we say, ooh, we want to create a record of stuff. Give me some space in memory. Don't care where it is. Okay, so this will come from what structure? What do we call it? H it began with. Heap. Okay, like your bedroom, if you're looking for something in your bedroom, you've got a heap in front of you. It doesn't matter how it's organised, you can find things, generally. Not that your parents think you can. So, in some place in memory, we get space allocated for this new item. We're going to store Dave in it. So this bit is the name part. This is going to be the link part. Okay. So I store that information. Now I need to tie it up with my list. So, and I'm going to do this all diagrammatically, and then we'll look at another way of representing all this stuff. What I do is I point the head at my new memory space where I've stored Dave. Okay? What follows Dave?
The link there is still
What is it going to link to? There's only one item in the list. What is it going to link to, do you think? Null. Nothing.
Oh,
Okay? So we've currently got, and if we want to traverse this list, we start at the head. What we're essentially doing is we're creating something that's sequential. Okay, so we have a head value that points to the first item in the list. We have the data item and a link to the next item in the list. Currently there is nothing else. Okay, right, I'm going to add step to the list. So I am going to again ask the operating system for some space. And when you draw yours, don't try and draw it neat, just draw it exactly like I'm doing, all over the place. Okay, for some of you that is like bread and butter. Right, so I'm going to put step down, not literally. Okay, and I want to add it to this list. I want to maintain alphabetical order. So if I search along from the head, I'll find that we've got Dave. Now, Steph needs to go after Dave. Remember Perry about the alphabetical stuff from yesterday?
I was tired.
Oh yeah, get out of it.
It's a Monday morning.
Yeah, for all of us. Right. Okay, so if we want Steph to follow Dave, the link just needs to point to Steph. Steph's got nothing after her, so we'll just put -1. Yeah? Right, let's add someone else. Gittis, because he'll be interesting. In this example, he would be interesting. Not in real life. And no one's got any comebacks to me. It's quite sad. Right, so again, I have asked for space to store the information about Gittis. In reality, we'd probably have lots of information in here. So we might have like some historical records about him. Okay, how many times it annoyed me in a lesson and things like that. Right, we're going to add Gittis to this list. Where is Gittis going to appear in this list?
Steph.
Not after Steph, it's got to be alphabetical.
After Dave, before Steph.
It's going to be, yeah, after Dave and before Steph. We can see that because we can see all the data. The computer can't do that, remember? So it would search from the start. We're effectively doing a sequential search. So we look to see if it's Dave. Oh no, Gittis is bigger than Dave. Better keep going. Ah, Steph's bigger than Gittis. So it must be before Steph. So the only thing we've got to do is say, right, well, who was pointing to Steph? Well, it was Dave, wasn't it? So we can break that link and we can just say, right, okay, then point that to Gittis. Where did Dave originally point to? Well, that was Steph. So we need to make Gittis's link go to Steph. Now the beauty of this, so that link's just broken. The beauty of this is, in order to insert something, all we do is we ask for the space and then we just change some pointers after a bit of searching. All we're doing is changing pointers, integer values. There is no hardcore calculations going on. Okay? Let's add someone else. Caleb. Okay? I like Caleb. So I'm going to create some more space. So I've asked the operating system, give me some space. Right, in this instance, where's Caleb going to end up?
Before Dave.
Nice.
Before Dave. At the head of the list, as we describe it. Okay, so we search and we go, whoa, the first item is bigger than Caleb. So what we do is you say, right, okay then, the head was pointing to Dave, so let's make that connection. We can then break that connection and point to Caleb. Insertion at the head of a list is ultra quick. There's no searching to do. Okay? We'll come on to that later on when we look at static dynamic allocation. Right, but essentially this is all that's happening. Right, let's say we've got bored of Dave now, we're going to delete him. Get rid. We don't physically delete the contents of memory where he is, but we do need to give it back to the operating system because we've had this dynamically allocated. We need to say we don't want it anymore, release it. What do you think we've got to do in order to remove Dave from this list?
We have to link the head to Gittis and remove Dave.
Yeah. So if we take look at Dave. Dave was pointing to Gitters. So whoever points to Dave, they need to point to Gitters, which is Callum. So do that. Do we need to do anything else?
Choose the memory
Got
card.
to stop the
Delete the
links
link
to
from
Dave.
Well, we don't need to change that link. We don't overwrite things in memory. We just say, yeah, put it back on the heap. That space is now available. You can allocate it to somebody else. They'll overwrite it. So we actually only need to change one pointer.
It's the link between Callum and Dave.
Well, I've just altered that. When I did that, that's effective. I've overwritten
Oh,
that
okay,
one.
so I've written that.
Yeah, I've overwritten that one. So that's gone. Okay. Now, if we didn't give that back, you can see that what we end up with is a blob of memory with nothing pointing to it. Okay, and that's a problem. And that's where you get these memory leaks. Not such a problem in a language like C#, which is what we call a managed language, where what happens, if you do this, from time to time there is a garbage collection system, okay, that looks round for allocated memory that has no links to it. So it'll look, is there a pointer to Dave? There's no pointer to Dave. Bin it, take it back to the heap. But that's inefficient. That can make the program just come to a grinding halt if you're allocating badly. In unmanaged languages like C#, C++, you have to do all this yourselves. So you find it very hard to get a memory leak with a C# program, but if you wrote a program in C++, you can easily do this. Okay, and obviously the more complicated the software is you're writing, the harder it is to keep track of allocating memory and deallocating memory. Okay, unless you're very, very religious about how you program. If you do it all sloppy, you're going to get memory leaks all over the shop. Okay, but in managed languages like C#, it will pick that up. It'll go, oh, nobody's using that. I'll collect that up for you. Okay. So when you're writing X and A games, that's all doing this all the time. So it can be a real big problem. Strings cause this problem quite bad. Strings are dynamically allocated in C#. You're not supposed to use it, you should use string builder. You know when you like doing concatenation? Every time you do a concatenation, you're building another string. It's really odd. It's just the way they decided to do it. Okay, so the nice thing about linked lists is it's very, very quick to remove something from a list, because all you need to do is change a few pointers. Yeah? Anyone got any queries about that? No? Right, I'll stop the bit so that leaves that as one thing. If I can remember how to stop it.